Hi fellow enthusiasts, welcome to my channel. Let's go into today's video and we're gonna come back at the end to wrap it up. So continuing this episode, we're working on multi-vibrators or 555 timer. Today we're going to look at the multi-vibrator. Last week we looked at the monostable and we talked about power up one shots. And today we're going to look at different aspects of this. So let's just recap what we did last week. We created this circuit called the power up one shot, and so let's just open it and do a quick review before we continue today. So in this simulation we did last week, we were able to demonstrate that if you put on the power here and start the simulation, let's just do that. Let's open this power and start the simulation, wait for it to settle down, and then we can turn on the power. And once we turn on that power, we notice there's a power up one shot here. Goes up, down. Now, as you can see on the input of the inverter, that's the blue line, it has the power up one shot, right? And the output of the inverter goes low first and then comes high and stays high because the output is low, the power up one shot. Why does this work? Because we have pulled down the trigger pin, which is pin 2, through a capacitor to the ground, and when power comes in, there's a jitter around the capacitor that makes it to short and gets it triggered, right? There's a comparator inside that is triggered. The output goes high, sets a flip-flop inside, and then gives the output high. Stays on until the time determined by R2 C2, and then that's when C2 charges up to 2/3 VCC, and then it will it will set the other flip-flop on, the other inverter on, sorry, and that inverter resets the flip-flop and you get a 0 or an output of 0 voltage. So the output of the inverter is 3.3 volts, but the input is 0. When the input is 1 or 5 volts, the output is 0 volts or 0. So let's turn this off. You can see again, we said last week that this inverter is powered from a different source because we didn't choose an inverter that has power supply, so that's why you see this here. But let me turn on the switch here, and as soon as the switch turns on, the output goes 5 volts, and then the inverter turns it to 0. That's what you see right about here. So if I remove the blue, let's see if we can turn that off and just see what let's pause this. If we turn off the blue meter, you will see the dip created by the green meter. So now today we're not going to be talking about this anymore. Let's just go to the schematic and create something new. We want to create a new schematic, and that will be for a multi-vibrator. So stop this. This is a monostable. We're going to create an astable multi-vibrator. So let's just create something new. Save changes. We made slight change, so save that and fail to save. Okay, we don't have to save it. Let's just create a new one. 5 timer Astable. All right. Okay, there's a problem with saving this. Maybe I didn't log in or what. Log in to save. Yes, I did not log in, but I see that I'm logged in here. So let's just create a new system here, a new circuit here. So for today, we're gonna do similar thing as we did last time. So we're gonna take 5 timer, We're going to take resistor and capacitor. So capacitor right there, resistor. I'll probably need an LED, so let's just take an LED for now. We need a power supply and ground. We need a power supply switch. We need a switch. We need a power supply. And I think this will be about it. If we need more, we'll grab them as the time arrives. So I'm gonna put the power supply right on the leftmost and then just wire it up. If I want to keep this wire down here, I have to click there before I drag it up. Otherwise, if I just keep moving, it will just follow me. So I want it to give some gaps. So I'm gonna click, then it stays there, and then I can go up and connect it up. Then switch comes over here, and then connect up, ground. Alright, capacitor. I'm gonna make a copy of the capacitor, flip it around. I should have drawn the circuit before we start doing this. So let me just draw the circuit. Let's draw the circuit out, and then we'll just start making the connections so that you can follow easily what we are trying to do here. All right, so we have the 5-5 timer. We have shown the pins before, but this will be pin 4, pin 8, and for pin 4, actually we're gonna pull it up with a resistor. And we're doing this on purpose. We can just pull it up straight, but we want to use this point for something later. We're gonna pull it up that way, and then we have pins 2,6 here, then pin 3 here. So that's 3 and threshold connected together, 1 and 5. So this will be 5, then this will be 1. 1 goes to ground straight, and then we're gonna have a resistor right here, but this resistor will connect to 2,6, and then 2,6 through a capacitor to ground, and then this. Okay, I'm gonna remove this resistor for now and this wire here, and I'll show you why. Because I want to loop this wire around, loop it around to 3, then the 3 will be output. So this pin 4, then maybe I should also delete this one here, because I want the resistor to show up here, and then this goes to my positive, then this goes to my 0 volts or my ground, then this is my output. This output I can connect it through an LED to ground as well, or 0 volts. This will be my R, and this will be my C, and my T on will be 1.443 over RC, and T off will be 1.443 over RC, so that my T is gonna be T on plus T off. Alright, just zoomed it so much. It's gonna be T on plus T off, so that my frequency is gonna be 1 over T. This is the 5-5-5 timer. So this is the circuit we're gonna create today, and then this point, of course, we're gonna connect something to it. We're gonna do some experiments with that connection. So this is what we're trying to create today. Just for beauty, Let's paint this LED red. Let's just pretend that it is red. Should have used a marker. It will highlight it faster. We already got most of it covered, so we'll continue this way. All right. So let's go back. So let's just analyze this. So this value can be anything. So from 1K, 10K. So let's just put 10K here. 10 kilo ohms resistor. In RC, whatever value we want to put, we're going to put it there. Normally what I do is I pick one and then I calculate the other. So we can call this 10 microfarads. Now we're using a simulator, so it doesn't really matter. You can also call this 10 kilo ohms. And then we can just play around and see what value gives us. This is 0.1 microfarads. All right. This resistor here could be 220 ohms, or you can also use 1 kilo ohms. All right, so let's create that circuit here. So we have one resistor here. This resistor, flip it around, it goes, connects here, and then it connects to pin 3. We're gonna try to make it look like we have in the drawing, even though the IC was not laid out that same way, but we're gonna try that and see if it works. All right, I need 2 and 6 trigger and threshold connected together. And then control voltage or voltage control. Let's flip this around. All right. Reset goes through a resistor. So for that reason, we're going to move this up a little bit and clone this resistor and just connect it there. Like we said, we try to make it look like we have in the outline. So pin 8 goes up, resistor goes up here. So LED, we need you down here. We need a clone of this resistor here. It's 1K already, so we're just gonna leave it as 1K. We're not changing that. I'm not a fan of connecting parts, four components in one spot, so I have to separate it this way. Pardon me for that, but it's just the way I like to design stuff. All right, so I can do 3 together, but 4 I have to give a gap to show that they were actually connected together. So I think we have everything we needed. We just need to change the values. So this one, let's just make it 10 times. Easy. This one will make it 10 times as well, more. And then for this, we're going to make it 10 times less. And this, we're going to make it 10 times more. So what's the value? 10 times more. I think we're good to go right now. So let's just put our meter. And let's start the simulation. And go split screen and see what is going on. Obviously 0 volts because we haven't turned it on. Let's turn it on. All right. You can see the Astable operation. The voltage is really out of the screen, so we can see the top of it. So we're gonna stop the simulation and change our settings on the voltage. So you just go here. Yeah, because it goes from minimum one picovolt. Let's just make it 0 volts and then do the maximum. We know it can only get up to 5, but we're just gonna set it as minimum volts. Minimum volts is, oh sorry, minimum volts should be 0. and maximum volts should be 5 actually, but we're gonna do it 10. um all right, so minimum is 0, maximum is 10. Yeah, that's no point doing it 10 actually. We can do 6, so we can just see the top of it and know that it doesn't exceed. Yeah, I think 6 is fine. So let's just run the simulation one more time. All right, you can see this is an Astable multi-vibrator. Always the first one doesn't seem to be the same as the rest. Always, even when we did the monostable operation, the first one just looks odd, and then the rest you can see. So you can see our LED is blinking on, off, on, off, on, off, on, off. And you can see the voltage here: 0 volts, 5 volts, 0 volts, 5 volts, and so on and so forth. Let's just zoom in and see if we're actually getting a square wave. I'm going to pause it at some point. Let's pause it here and just examine this. It looks like a pure square wave. Yeah, looks like a pure square wave. The angle is near 90 degrees. So I'm just trying to drag this to see. Yeah, really it looks like a pure square wave. You can see it's like 90 degrees, right? So it starts from 2. So let's do the math here and see how what's our on time and off time. So it starts from 2.6745 and ends at 2.7437. So there's around 0.0692 seconds. 69 uh milliseconds, 69 milliseconds, 69.2 milliseconds is the on time. And let's check the off time. So 69, we did 69.92. So off time, it goes off at this point, so which is 2.7439, and it goes on again at 2.8129. So this is exactly 69 milliseconds. So on time and off time are the same. You can check it throughout. On time and off time are the same. We can also check this one here. Um, let's do this. 2.8134. That's when it gets on and it goes off, it starts going off or negative going at 2.8824. Exactly 69 milliseconds again, and so on and so forth. So the theory we had at the beginning when we looked at this is actually accurate. So on time is equal to off time, and so the total time or the period is T on plus T off, and that means our frequency can be calculated from that. So if the on time T on is 69 milliseconds and T off is 69 milliseconds, then T is 138 milliseconds. So that frequency 1 over t is equal to 1 over 138 times 10 raised to minus 3. So the frequency 7.25 hertz. 7.25 hertz. Is that the right math right there? Right. I think that should be about it. Okay. So let's go back to our simulation and see why we had that wire in our drawing. There's a wire in our drawing that we didn't really talk about anymore. This thing here. We need to really address this. So what is this all about? So let's go back to our simulation and take care of that. So we'll turn it on one more time, run, and we can just see this is amazing. So I'm gonna stop it. Schematic. And can we clone this? Can I clone this? Copy. So all I did was do Control A to copy all, to select all, and then I did copy when it showed me the option to copy. So I've just cloned it. I'm gonna delete this power supply, and I'm gonna use the same power supply. There's no point having two. It's gonna have the same power supply, and then we will connect the same output here. We connect the same output to the reset pin of one. So this one here will reset the other. So let's just take something from the output and connect it to the reset. So how do we do that? We're just going to take something from here and then go and connect it to this point. Right. So I think this might create a conflict. So to solve that, avoid that problem, let's just put a diode here. So this diode makes sure that the voltage goes only in one direction. It doesn't interact with the DC condition of this other section in terms of going back and influencing the diode here, because I have an LED here. Let's do two things. Let me remove that diode first and just run the simulation and see what happens. So this LED is on, always. Okay, no, it goes off too, and both of them go on and off at the same time. Basically we have the same circuit. So let's make this different frequency. Let's change this by 10, factor of 10. Alright, and both of them are going to go off at the same time again and go on at the same time again. And the reason being that this is trying to reset this one here. Alright, so this goes on faster. Let's see. So while this is on, while A is on, so we're going to call this section A, and then that's section B. While A is on, B can flash multiple times, but while B is off, A is always off. While A is off, sorry, B is always off. I'm going to explain why when we go back to the one note. But you can see, let's just wait one more time. Right now, A is off, B is also off. throughout the period that A is off, B is off. Now A is on and B is on, but B will go off, on multiple times as long as A stays on. As soon as A goes off, B goes off. So let's go and explain that, because that's the purpose of today's tutorial. So the 5-5 timer has the pin number 4 as the reset pin, and we said it is an active low reset pin, which means when you ground it, when you take it low, it becomes active. That's the meaning of active low. Active high means when you pull it up, it becomes active. Now this is active low. That's why when you write it as reset with a bar on it. It means active low. When you take it low, so when you send it a low going voltage, there's when you reset it. So it just starts afresh when you remove that voltage. It will restart. So this explains why when the A section, and we're just gonna call this B. So when A is high, so that will be this point. When A is at this point, high or on, high 1 or on. When A is at this state, this reset is not active because the pin is an active low pin. So it's not active. So B functions as it should, and hence the output of B continues to oscillate. Multi-vibrator vibrates. Now when A is in this state, which is low or 0 or off, right? When it's in this state, then B is reset. This is pulled down, pin 4 is pulled down, and the output of B remains flat out 0. So if this is voltage and this is time and this is at 0 point, output of B remains flat out this way. For when this is again maximum V max, and this is time, and then these are the various outputs. So basically what we've shown here is that when A is on, B is free to function as it should because the reset pin is not engaged, is not active. However, the moment A goes off, the reset pin of B gets engaged and it becomes active, and because it's active, every activity on B stops until that pulse goes back from negative or from 0, from off to on or 1 or high. So I think yeah, so we can just add positive to it, and then for this one we can just add negative to it. So any of these states, low, 0, off or negative, will ensure that B is turned off. But in any of these states where the output pin 3, which is pin 3 here, when it is high or 1 or on or positive, then B is free to function the way it should. Now what you can do is to determine the frequency, and I've given you the formula. The formula is formula for frequency. F is 1 over T, and T is T on, small t on, plus small t off. So that's how you get that. And T on is equals to T off in the configuration we have. So it's a 50% duty cycle multi-vibrator, stable multi-vibrator. So in this case, T on is equal to T off is equal to 1.443 over RC. And to explain this a little bit, so let me just leave this for a second so you can get the formula. F is 1 over T, that's total time, and total time is T on and plus T off, and T on is actually just the on duty cycle, and T off is the off duty cycle. So which is basically the time it stays on. So the time is going off. This is your T on. When it goes off and then stays off for a while and comes back up, this is your T on. And we found out that apart from the first time we boot this up, according to this simulator, the rest of the pulses are 50% duty cycle, shared 100%, shared between on time and off time. So, and it goes on and on and on. We calculated based on our values. Well, not calculation per se, but just looking at the graph that we plotted, that this is the number of time it takes for each one. But we can actually do the recalculation to say that T on or T off is equal to 1.443 divided by RC, which is the same thing as 1.443 divided by R is 10 kilo ohms, 10,000 multiplied by C is 10 microfarads, 10 times 10 raised to power minus 6. So let's do that and see what it gives us. Let's do the math here. So 10,000. So actually we can just reduce some of these zeros. 1, 2, 3, 4. We reduce this to minus 2. So it's going to be 1.43443 divided by 10 times 10 raised to minus 2. Alright, and we can just multiply both sides by 10 raised to power 2 so that we can move these two zeros. So 1.4, sorry, it's going to be 1443, 144.3 divided by 10. So really it's going to be 14.43. So T on in reality should be 14.43. So let's just make sure that the calculation works fine. I'm going to get a calculator. So let's do the calculation here. So we're dealing with 10,000 multiplied by we're going to open a bracket here, 10 times 10 raised to power, no, all right, so we're dealing with 6 minus 6. All right, so 1 2 3 4 5 6. All right, but that's 1, so we need 10 multiplied by 10 multiplied by 10,000. Yeah, that's what we're looking for, and we're saying this is going to be dividing 1.44. So 1.44 divided by that. So we were right. So the calculation was right. So 1.443 divided by 0.1. Remove this one, remove this one. So we're right. All right, so we didn't need a calculator anyways. So that's the T on, and then T off is the same. So multiplied by 2, that will give you, so 28.88, 0.86, 28.86. So we're doing 14.43 times 2. Oh, I did times 3. 14.43 times 2. Yeah, and then 1 over that. That's why I brought it over here, because I want to do an inverse of that. So the T on and T off is this value, and the frequency is actually less than a hertz. It's less than 1 hertz. So it's like this 0.03 cycles in 1 second. So it's the frequency is less than 1 hertz. So what we measured from the simulator is not the actual thing that we measure in real life when we calculate for the value. So let's go back and look at our simulator. So here we did 10 microfarads and 100. Sorry, this is the one here. So 10 microfarads and 10 kilo ohms, and the duty cycle should be 28. The full T on plus T off, which is the duty cycle of this, should be 28 uh 28 seconds based on the value that we have chosen. Should be around 28 seconds, 28.86 seconds. Right. So do this in your calculation too, and I did this because when I was looking at the values, I was expecting something more, but the simulator was showing us something different. I think it can just do its best. Now let's look at this here. This is important. Now all the time that the green is on, which is A, the section A is on, B can be on and off at several times, multiple times. But the time that A goes off, B stays off throughout that period and waits again until A goes on. And again, always every first pause, every first high going pause of B is always always has a longer duration. It always has a longer duration compared to the subsequent ones. Maybe the time it takes to charge the capacitor the first time from empty, from nothing, to 1/3 VCC, and then it never really discharges below to 0 throughout the rest of the cycle, right? It just oscillates between 1/3 VCC and 2/3 VCC. It never goes to 0. But when it's off, it has enough time to discharge, and then when you start again, it takes a little bit more time to charge it to the threshold, and then it starts to oscillate one more time. So we can go here and play around with the values of this resistor. Let's increase it one more time, and because we've increased to 1 meg, the on time will be longer. The on time will be longer, and then B can oscillate much more times. Let's just drag this over so you can see B can continue to oscillate many more times than A. You see, I can, when I close it, reduce it this way, you can see the effect. The previous ones were just close together, but because I've increased the value of R1 and also the on time has increased, remember it will be the same as the off time. On time of A is increased, and now allows my B to oscillate multiple times, much more multiple times. Now, what can you do with this? We're going to cut this off in a few minutes. What can you do with this? You can try to design a D door. I think they call it D door tone. The police alarm. Or you can design a busy tone, ringing tone for one, and a telephone. You make your B here, the one I'm showing you right here. You make your B to oscillate at audio frequency range. So between 200 hertz to 20 kilohertz. Make your B to oscillate in that range, and then use your A to control the on time and off time. So A could go on like we have now for a long time, while B goes, gives a high pitch and repeats that, like, and then you pause it. You cut that off by connecting uh, the low going port from A to it to the reset pin, and then you cut off the audio. Just as we've cut off the LED, you can cut off the audio. If you connected a speaker here, you will hear sound here. You cut off the audio, and then when A goes back on, then B can oscillate again. So you can hear like wow, wow, dee do, something like that. So the D being the high pitch, the audio frequency, and then the A will be cutting it off. So instead of going steady, like let's say the pitch is like P, let's say that's the tone you generated. Instead of going P forever, you can make it go beep, 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 like beep, beep, beep. You can make it to, you can vary it to, different tones. So next week we're gonna do that in practice. In the next video, we've built up a few tutorial now, so we can just go ahead and do the video demonstration, not just the simulation, because the simulation is not it's not the full demonstration, right? You can see a theory, you can see something that could work when you run a simulation, but after that you have to build it to see it work. You have to build something. So that's what we're going to do next week. We're going to build something so we can see what we've demonstrated the theory to work. We're going to start again with the monostable or the power up one shot, and then we're going to migrate from there and build the astable. So this is about to come up now, because the time, it's about right. 1 2 3. So 1 2 3. It's gonna turn back up. Yeah, it has just turned back up, and then it will stay the same time period, and then it go back down. So all right, so I won't wait for it to get to the next one, so I'm just gonna reduce the value here. You know what, why don't I reduce the value of the capacitor? Yeah, let's reduce the value of the capacitor and see the effect. All right, so maybe reduce it a little bit more, so make it faster. Yep. All right, so I've just created an interesting problem here. I don't know if you noticed that, but the interesting problem is I've made A to oscillate much faster than B, and if A oscillates much faster than B, then it's hardly gonna keep B down, or maybe you won't even see B anymore. I'm making A oscillate much faster by reducing the value of the capacitor. So you should always have B oscillating much faster than A. All right, so it's hard for us to notice B going down or something like that. So let's just do the right thing, according to Russell Peters. Do the right thing. All right, so let's reduce this 100k. Now we are within the realm of doing the right thing. 100k and 1 microfarad. So let's increase this to 10 and reduce this to 10 as well. Now it's matching our, let's just look at B and make sure it's matching. 10, 10 and 10, 10 and 10 is matching. So what I'm going to do is to then play around with this, reduce it, so we can see the output. All right. Now you can see the effects. Yeah. All right. So this is higher frequency. So you can play around and get higher frequency, and you see it oscillating much more time within that window, and so on and so forth. I'm going to even make it go even faster by reducing the resistance even more. No, let's not do that. Let's reduce the capacitance. Let's play with the capacitance. So I didn't want to change that. I just want to change the value of the capacitance. All right, so let's reduce it more, and we'll see the effects. You can see that right away. Higher frequency. All right. I am going to zoom in so you can see that it actually goes on and off, not just a continuous stream of blue lines. See, it goes on and off. Right, now I'm going to reduce it even further. Now you can see how compact it is. That just shows you the frequency, the change in frequency. It's like a continuous blue stream here, but no, it's actually some on and off periods. I'm just zooming in to show that. Now I'm going to reduce it even further, 10 nano. So if you want to get the frequency even higher, so I'm just zooming out to show a bigger picture of it, like a broader view. But let me zoom in. Right. So I can also reduce further. Let's just reduce further. I'm going to keep this in view so we can see, have a comparison. So let me reduce it further. Further, 1n. This is going to be crazy, right? The frequency is just going to be crazy. All right. So do this, go to multi-sim and create. Let's just give this a name. All right. Build this yourself. Go to multi-sim, create a free account, and start playing around with this. In next episode, we're gonna have physical 555 timer and build a circuit like this. You can also play around with the control voltage for the audio section. You can connect. Let's see if we connect. Yeah, let's do something before we go. Yeah, I forgot about that. This diode, we want to place a diode right here. Nope, that's not what we wanted to do. We wanted to place the diode right here. Yes, and we want to see that it has the same effect. When I had the concern that there might be interaction between DC bias condition of B and A because it goes to the output of A, I wanted to put a diode, and you see the effect is the same. No, it's not really the same because when it's going low, yeah, it's not really the same. It's not really the same. It just lets it run because when it's going low, it doesn't really let it go low, right? This should have been dragged low. So let's see. Let's stop it. Take this out. Yeah, we didn't get the effect we wanted. B continues to oscillate. A goes on and off. Not a problem at all. So let's just flip this around and see if that solves the problem. That's what we can get with simulation. So you don't have to build this out, only for you to find out that that doesn't work. All right. So we're trying to sync the voltage here. We'll try to sync this pin when B is actually when A is actually off. So let's see if that works. And if it doesn't work, then we've seen what doesn't work. All right, so that works. So we've shown how to connect the diode. If you want to use a diode, then you have to connect it backwards this way. So when A is on, it really doesn't interact with with the B, and when A is off, it sinks the voltage and as well sinks B, right? And I think this resistor here does a good job for us because it actually offers some resistance. So what if I reduce the value of this? Let's see the effect to 1K. Let's make it 100 ohms, 10 ohms, 1 ohm, 0.1. All right, really, it doesn't do much, but in practice, I'll just put 10K there. That's one thing I wanted to show. So we don't need this resistor here. So let's just remove it. We don't need the diode, sorry. So we're gonna remove the diode. All right, we don't need the diode. Let's try to connect the output. We don't also need this for now. So we're gonna remove this. We don't need it anymore. Let's connect up the output to the control voltage and see the effect. I would actually connect a switch to it so I can see what happens with the switch. Okay, so let's run it, and let me just turn the switch off. All right, you see, when I turn the switch on, it's modulating the output of B. It's changing the duty cycle. When I turn it off, it goes higher. So you can use this value to make it go to alter the audio signal coming from B. So let's turn it on again. In this case, I'm going to go back and try to change the frequency of A and see the effect. So I'm going to change this by reducing the value. Right now that I've reduced the value, let's see. And it's basically the same, 10 and 1, 10 and 1. So basically the same. And we can see any notable difference. Really, I don't see any notable difference. So let me reduce the value of this capacitor. So I'm making it 100N. So let's turn it on. Alright, you can see the effect now. So when I turn it off, when I turn it on. So play with this and see the effects that you get. We'll play around with all this next week. So don't miss that video. We're gonna have the speakers connected, 5 timer connected, configured in this way, and then we're just gonna play around with the reset pin and the voltage control, and we will make some tones that we're gonna enjoy. All right. All right. Thanks for sticking around to the end. That'll be it from us today. Please, if you have not subscribed, do so right now. And don't forget to like and share this video. Until we come your way again with more contents, stay enthused.